In this video, we're going to talk about operations with functions. We've already did an extensive study of the functions in our library of functions. And so we found that we could take those functions in that library of functions and we can transform them by either adding, subtracting, multiplying, or dividing a number or numbers in different places to that function. Well, in order to get even more complicated functions, we can add multiple functions together. So we might take a square root function and add it to a cube root function and get a more complicated function or things of that nature. And that is the goal of this section here. How can we combine functions together in some sort of a way to get other functions, and what happens to the properties of those functions, be it the domain, the range, things of that nature, when we do those combinations. And so the algebra of functions, it says let f and g be functions with domain a and b. All right, so I already see that I have something wrong in this box here, but we'll correct it here. Then the functions f plus g, f minus g, f times g. So notice when we don't see an operation between two functions or two things in math, we assume that it's multiplication. So that's f times g, and f divided by g are defined as follows. F plus g of x, you just take the algebraic expression for x and add it to the algebraic expression for g, right? So addition, subtraction, multiplication, and division are arithmetic operations. They are done to numbers. Not only are there arithmetic operations, they're also operators. Those are things that are done, operations that are done to actual functions. And so basically what we're going to do is we're going to add the the algebraic expression that represents the functions. We're going to add those together and try to combine terms in some sort of a way when there's addition. For the subtraction, we'll just subtract the two algebraic expressions from each other. When there's multiplication of two functions, just take their algebraic expressions and multiply them. And when there's a division of two functions, you just divide the algebraic expressions. So that's kind of almost like common sense. What we will be focusing on in this section is what happens to the domain of those functions when we add them, subtract them, multiply, and divide them. Well, with addition, subtraction, and multiplication, the domain of each of those functions is basically going to be the intersection of their individual domains. And by intersection, in math, sometimes we use the union symbol. It looks like this, but in words, it's the union symbol. Well, the intersection symbol looks like that. That means if I have two sets of numbers and I want to know the intersection of those subsets, it's got to be in both of those sets of numbers, right? And so the upside down union symbol is the intersection. And for instance, the intersection symbol represents the word and, whereas the union symbol represented the word or. All right. So whenever we see an and, we have to make sure that whatever our intersection is, it includes elements that are in both. And if it's an element that's in one set but not the other, then it can't be in the intersection. For instance, if I gave you some inequalities, right? Let's say I want to do the intersection of the inequality x is greater than or equal to 0, and I wanted to intersect that with x is less than 5, right? So if I look at this set right here, x values that are greater than or equal to 0, I'm going to come here, put my 0 in. I use a closed circle because that's an equality there, and I shade in values to the right because those are values that are greater, right? That's 0. I'm going to put this one under this other inequality for x less than 5. I'm going to put this under here. So let's say 5 is over here if this is 0. I'd use an open circle at 5, and I include all the values that are less than. And so if I could take these two sets and find an intersection, what will basically happen is I would have an overlap of these two number lines, and wherever the shaded parts are overlapping, those are going to be the values that are in my intersection. And so values that are in my intersection are going to be, well, I have to have 0 because 0 is in both of them. And all these values all the way up until I get to 5 is going to be in my intersection, but I can't include 5 because if it's not included in this one, then it's not in my intersection. So I have a closed circle at 0, and then I'll continue all the way until I get 5. And so my intersection would be from 0 to 5, and I put a parenthesis around 5 since I don't include that. That is the intersection. That's what we mean by the intersection. And so when I add, subtract, and multiply two functions, the domain of that sum, that difference, or that product is just the intersection of each of those domains. All right. The difference when we have division is the fact that we could potentially divide by 0. So it's still going to be the domain of f intersected with the domain of g, but we also have to intersect it with the fact that g of x cannot equal 0, or the set of x values that make g of x equal 0. All right. And so let's look at this. We just have this extra, again, we just have this extra little piece when we have division, but pretty much all of the domains are the same. All right. So let's get used to doing these, the algebra of functions, addition, subtraction, multiplication, and division of functions. And so we have f of x equals the square root of x, and g of x equals x minus 4. Just for fun, I'm going to go ahead and think about what the domain of f and g are, even though I don't need it for part A. But when I look at this function, f of x, this is a parent function. It's a function in our library of functions. It's our square root function. And what you should remember is that whatever's under your radical has to be greater than or equal to 0. And so since I have x under my radical, then the domain of that function is x is greater than or equal to 0. Or we can write that in interval notation as 0, infinity, right? And so when I go to g of x, notice that that's a linear function, and the domain of any linear function is all real numbers. So it's from negative infinity to infinity. So this is the domain of f, this is the domain of g, okay? In part A, we want to find f minus g of 4. Again, I could rewrite that as f of 4 minus g of 4. Okay, sorry about that. And so f of 4 just means go to your function f, plug in 4. G of 4 means go to your function g, plug in 4. When I do that, I'm going to get a 2 minus 0, which is just 2. All right. F plus g of x. Well, that's saying, oh, take your expression for f of x and add to that the expression for g of x, right? And so my f of x is the square root of x. My g of x is x minus 4. Can't combine any like terms. So this is what f plus g of x equals. Now I want to find a domain in parts B, C, and D here. So let's find our domain. Well, we already know that it's going to be the domain of f intersected. Our domain of f is from 0 to infinity, intersected with our domain of g, right? So I'm actually going to do some stuff on our number line here just so that we can see this. I have to always do this, but I'm going to do 1, 2, 3 number lines, right? This first number line represents f, the second number line represents g, and then the third f plus g. And we're going to look at their domains. The domain of f is from 0 to infinity. So if I put 0 on that number line, I know I'm going to have a closed circle, and I'm going to shade all the values to the right. 0 to infinity, x is greater than or equal to 0. The domain of g is all real numbers. That is my entire real line. Sorry about that. And so if I want to intersect these two, then it's got to be where they overlap. Well, it only overlaps where the shaded parts overlap. And the shaded parts overlap for x values greater than 0. And I get to include 0 because it's included here. It's shaded in here. So my domain of my final function will be from 0 to infinity, basically, which is the same thing as the domain of f. And I can't change colors for some reason. There we go. And so the domain 0 to infinity. All right, let's do f times g of x. F times g of x. Well, for us to figure out what f times g of x is, we take the expressions for f times g and we multiply them by each other. So I'm going to take that square root of x And I'm going to multiply that by my x minus 4. And so what we have here, let's make sure we did that, third of x times x minus 4. And this is actually a good simplified form. Remember, you could simplify this by changing this to x to the 1/2. And then when you use your distributive property, remember this is the first power. And so 1 plus 1/2 is 3/2. So you could write this way, right? But either one of these works. And basically, we already know the domain because if we know the domain of when we added the two functions together in part B, then we get the same domain when we do the multiplication. And so the domain is still going to be from 0 to infinity. And so we're done with that one there. In part D, we have f of x over g of x. So here, what we're going to have to do is we're going to take the expression for f of x and divide it by the expression for g of x. All right, so the expression for f of x was the square root of x. The expression for g of x was x minus 4. Now, that is completely simplified because we have a subtraction in our denominator. So I wouldn't do anything to try and further simplify this, right? However, we need to find a domain. Now, we know that the domain of f intersect g is from 0 to infinity, right? So I already have that piece here. Now, 0 to infinity. All right, that's the domain of f intersected with the domain of g, all right? That's the domain of f intersected with the domain of g. But when we have a division by 0, we have to make sure that our division by 0 is included in this intersection as well, right? When we divide by a potentially 0, we need to find what x value we substitute in for x in order to help us get 0. Now, in this example, you probably can look at that and tell that it's 4, but you don't want g of x to equal 0, right? And so what I like to do is say, oh, whatever g of x is, which is x minus 4, I don't want that to equal 0. So if I solve this equation for x, I'm going to see that I don't want x to equal 4. So with that intersection that we already have, I need to make sure that I exclude x does not equal 4. Now, if I were to draw g of x does not equal 0 on our number line, now we rarely ever do this because sometimes it seems pointless. But this includes all real numbers except x equals 4. All real numbers except x equals 4, right? So it's the whole number line except x equals 4. So I need to intersect this number line with almost everything shaded except for 4, with this number line that has from 0 to positive infinity shaded, right? So it overlaps at 0 and all of these values until we get to 4. So 4 can't be in the domain because it's open here. And then I include all the values that are bigger than 4. And so my domain in this case is going to be 2 sets. My first set is going to start at 0. And it's going to go until I get to 4. Since I have an open circle at this 4, that means I don't include it. That means I use a parenthesis. But I can use values that are bigger than 4, so I'm going to use another set. Remember in math, whenever you use more than one set to identify your solution, then you use the union symbol. I pick up very close to 4, but greater than 4, and continue to positive infinity. That is where these two number lines overlap. That is where x values greater than or equal to 0 intersect with x does not equal 4, all right? This is how we write it in interval notation. So this is the domain of f divided by g. Right. Notice how in these 3 examples here, we went from having some basic functions, square root of x, x minus 4, to having more complicated functions by doing an addition, by doing a multiplication, and by doing a division, right? So this is how we just build our math knowledge, right? Just add, subtract, multiply, divide things, and we can get more complicated functions. In addition to that, we can do what we call a composition of functions. All right, a composition of function is basically the process of having the output of one function as the input of another function. In other words, we're putting a function inside of another function. The way this works, let's say we have a function, a set x, right? We're going to take all the elements that are in the domain of a function g, all the elements x, apply the function g, and then we get to this set here, which is g of x. And then what we're going to do is we're going to take those g of x's, let it be in the domain of f, and we're going to apply the function f to it, and then we get f of g of x. So there's that function within a function type of scenario, right? And so what we want to do is we want to be able to combine functions together to get more complicated functions or more interesting functions, and the composition of functions allows us to do that. When we think about the compositions of functions, we have to think about the domain, all right? So this is the notation for the composition of functions. This is not a zero, it's a composition symbol. F composed with G evaluated at X, or F, it translates to doing F of G of X. G of X is what we call the inside function, and F of X is the outside function. All right, the inside function is applied first to your input values, and then those output values of that inside function get applied as the input values of your outside function. All right, so when we see F composed with G this way, we write F of G of X. You can go the other direction and do G composed with F evaluated at X, and that's G of F of X. When you write it the first way, your domain of your composition, your composite function is the elements that are in the domain of G, for which G is in the domain of F, right? So you got to be in the domain of G first to get to here, and then G has to be in the domain of F to get there, right? And so that's how we calculate our composition of functions. Let's look at an example where we do some with numbers and then we do some with other things. By the way, we're not going to find the range. We're just going to find the domain. All right. So we have F composed with G evaluated at 4, right? This notation means do F of G of 4. That means to go to our function G, plug in 4, right? So that's saying do F of the square root of 4. Well, the square root of 4 is 2. And now that I have that simplified, I'm going to go to 2 and plug it into my function f. That's 2 minus 2, which equals 0. Okay? Our next example, G composed with f evaluated at 2. That means to do G of f of 2. That means I'm going to go to my function f, and I'm going to plug in 2 wherever I see my variable x. That simplifies to a 0. And so now I go to my function G, I replace wherever I see my x with the 0, the square root of 0 is 0. All right? And that's that. Now we're going to look at how we can do the actual composition. And I'm going to slide this up slightly so that I can see my actual functions, right? So this is saying do f composed with G of x. Which means I take the algebraic expression for G, which is the square root of x, and everywhere I see an x in my function f, I'm going to replace it with that square root of x. So I'm going to have this equaling the square root of x minus 2. Now I want to find the domain of this function. We're not going to take the time to do the range in this video, but let's find the domain, right? So when I find a domain, what I do first, all right, and I know you're probably going to be like, well, why are we doing this, Mr. Pompey? Because you always need to check this. I'm going to show you an example of how we need to check this in a little bit. You need to find the domain of your inside function first. Every single time you do a domain of a composite function, because it has to be in the domain of that function. Sometimes the square root of x may not show up in our final answer, and if that happens, then we're going to run into an issue where our domain of the function that we end up with, we're not going to be able to pick up that square root was in there. So I always say to my students, go back to the domain of your inside function first. Since my inside function was g of x, and g of x was the square root of x, the domain of that, remember, you take whatever's under that radical and set it greater than or equal to 0. You can do a number line or whatever. You'll find that that's from 0 to infinity. Then what I tell my students to do is to look at your final simplified version of your composite function. All right, the final composite function. This composite function also has the fact that you have the square root of x and then you have a minus 2 there. So if I look at my final answer, it has a square root of x, right? And when I look at that, I know that x has to also be greater than or equal to 0. And so when I do my domain, I have to take whatever my domain of g was and do the intersection of that with the domain of my final answer. Well, since they are the same here, then the domain of my composite f composed with g is just going to be x is greater than or equal to 0. Or in interval notation, we're going to say 0 to infinity. This is my domain. Now, it made it seem like I didn't have to go through this process of doing my domain of g first. You always need to do this. You always need to do this because sometimes things simplify. And so if I didn't see the square root of x right here, and let's say that my function f squared that in some kind of a way and the square root went away, then if I just look at my final answer of my composite function, then I'm going to lose the fact that I needed to have x values that are greater than 0. Because if that was just an x minus 2 there, I wouldn't have had this part to remind me, oh, I got to have x values greater than 0. So always look at your domain of your g, and then look at the domain and intersect that with the domain of your final simplified answer, and that's going to give you the domain of your composite function. Let's go to part D. Here we have h of f of x, right? And so my function h was 1 over x up there. We hadn't looked at that one yet. But I'm going to take my x minus 2, which is my function, my expression for f. And everywhere I see an x in my function h, I'm going to put x minus 2. So I'm going to get 1 over x minus 2. And so what I'm going to do, I'm going to find my domain. First of all, look at your domain of your inside function, which is f. Your inside function, that's a linear function. The domain of any linear function is all real numbers. And now I'm going to look at the domain of my simplified composition, which is x minus 2. It is in a denominator, so I don't want that to equal 0, right? That means x cannot equal 2. When x cannot equal 2, that's basically negative infinity to 2 union 2 to infinity. And so what we have to do is we have to intersect your domain of your inside function with this piece right here. So remember, negative infinity to infinity is your entire real line. And if I want to intersect that with a real line that has 2 skipped over and includes everything else, then the intersection is going to be almost, well, basically everything on both of these lines. And the things that are on both of these lines is everything except x equals 2. So my domain of my composite, which is h, not f, composed with f, is negative infinity to negative 2, union 2 to infinity. Just so you guys are aware, we're going to do another example here. I'm going to do, let's say if this is E, let's do h composed with h evaluated at x. Remember, h of x was 1 over x, right? So that's h of x. That means I'm going to take my 1 over x and replace it wherever I see an x here. Well, there's a 1, and instead of writing this x, I'm going to put this 1 over x right there. So that's 1 over x. Well, 1 over something is its reciprocal, so the reciprocal of 1 over x is x over 1, or we just get x. So if I look at just this final answer here, it looks like this is our identity function whose domain is all real numbers, right? However, I always say do the domain of your inside function. My inside function is h. If I look at h, it's 1 over x, right? H of x is 1 over x. That domain is from negative infinity to 0, union 0 to infinity. When I look at the domain, my final answer, it looks like I have a negative infinity to infinity. So if I intersect these two, I get the domain of h composed with h, which is going to be from negative infinity to 0, union 0 to infinity. Okay? So the rest of the stuff that's in your notes, I am going to stop this video here, and we'll get to the rest of that stuff that's in your notes in class. So I'll see you in our next video.